Hello and welcome to Science. I'm your robot teacher, Mr. Turner, and we're going to be learning a little bit about greenhouse gases today. So, the two big questions I'm going to try and answer today are what are greenhouse gases, try and explain to you what the common ones are, and how they're affecting our planet. In the picture that you can see in front of you, this is a picture of planet Earth. I'm not going to try and tell you, some of you guys, that the Earth is round. You should know that already. But you might not know that this little blue layer here is the Earth's atmosphere, and it's pretty thin, but consists of a mixture of different gases. So if you, next time you blow up a balloon, you might want to think about what gases you're putting into the Earth's atmosphere. It's a little pie chart that just shows you what that mixture is made of. So it's about 78% nitrogen gas, the big blue section there, over 3/4. Nitrogen gas is not really what we're focusing on today, but it makes a big part of the air. 21% oxygen, that's really important to us. So talk about that in a second, but yeah, it's pretty important that planet Earth's got plenty of oxygen for us to breathe in. And then this is really important, 0.04% carbon dioxide. That's one of the greenhouse gases we're going to be talking about today. And the rest of the atmosphere, whatever it is, adding up to 100%, is made up of a few other gases, mostly in very small quantities. So let's have a look at those gases then. Top one, nitrogen. Nitrogen is made of two atoms of nitrogen. That's called a nitrogen molecule. When the two atoms join together, we call that N2. And nitrogen is really important for building all kinds of different plants and animals. We're all made of quite a high percentage of nitrogen atoms. So if you want to have living things on a planet, then you're going to have some nitrogen gas from somewhere to build them from. Oxygen's another major gas in the atmosphere, in the mixture. It's made of two oxygen atoms joined together like this, and that's what we call O2, an O2 molecule. And oxygen's so important for us animals because we take the oxygen inside ourselves and use it to release energy from food molecules. So when we have some food, you've got to have some oxygen to react with it, and that releases the energy from your cornflakes or whatever you've been eating. Okay, so these two gases seem pretty good, helping to build living things, helping to get us some energy, keep us alive here, us animals. Now, plants don't need oxygen, by the way. But these gases, the next two gases I'm going to show you, not so good. So carbon dioxide. Carbon dioxide is a gas that is made of one carbon atom and two oxygen atoms. It's called CO2. You'll hear me say CO2 quite a lot. That's why it's called CO2, because it's one carbon and two oxygens. And yeah, causing a lot of problems, which we're going to go into in today's lesson. And not only that, it's hardly any of it there. 0.04%, that's not very much. But it's, yeah, tiny sliver of the mixture of gases that's in the atmosphere, but it's causing some big problems around the world. And then the other naughty one is methane gas. And this one here, the little picture shows you that it is made of one carbon atom and four hydrogen atoms. It's a molecule of methane. It's called CH4, if I just get my head out of the way. And this one is also pretty bad times. These last two are called greenhouse gases, so that's the focus of today's lesson. Methane gas is, there's hardly any of it in, it's a very, very small percentage of the mixture here. 0.00017% of the Earth's gases are methane in the atmosphere, so not very much. But yeah, it's actually even worse than carbon dioxide in terms of causing climate change around the world. So it's one that is worth talking about because it's quite a major contributor. So even though there's not very much of it, because it is having quite a big effect, so that's why I'm adding it to this lesson here. So carbon dioxide and methane, why are they so bad? What is the problem with these two little gases here? Okay, so we need to talk about what warms up the planet and what cools down the planet before we can explain what's going on with these gases. So we've got a big star in our solar system called the Sun, and the Sun sends planet Earth its energy in the form of something called solar radiation. So this is it. You can call it sunlight if you like, but only if you're at primary school. If you're at secondary school, you shouldn't be talking about sunlight anymore. You should be talking about solar radiation. So here it is, solar radiation coming along from the Sun, coming along. When it hits planet Earth, it causes planet Earth to warm up because it's basically giving planet Earth some more energy. and everything that it hits will increase in temperature. So that's a pretty good thing, because otherwise planet Earth would be, if it was stuck outside with no sun in space, planet Earth would be absolutely freezing and not be able to support life whatsoever. So we get solar radiation coming from the sun. That's a good thing. Here's a man enjoying a little bit of solar radiation. You might remember that you used to be able to visit the beach before lockdown and enjoy a bit of solar radiation for an hour or two. Now, when the Earth is nice and warm, nice and toasty, when nighttime comes, the Earth starts to cool down and lose some of its heat energy, lose some of its temperature, and it loses its heat energy by giving out radiation. So not coming into planet Earth, but going away from planet Earth. This is not solar radiation, this is a different sort of radiation. It's called infrared, and you might have seen special heat cameras that can see in darkness because they detect the heat coming off of things. That's also something that detects infrared radiation. So it's the same sort of radiation as that. Anyway, so the planet Earth gives off infrared radiation all the time, but you notice it more at night time because there's no sun around. And that's the way that the Earth keeps itself cool, cools down. If it didn't lose this infrared radiation, then, just flipping back one, then obviously the solar radiation would just continuously heat up planet Earth and it would just get hotter and hotter and hotter. So there's a balance there. The solar radiation heats up planet Earth and the infrared radiation escaping will cool down planet Earth. So this is where the greenhouse gases come in. Greenhouse gases form a layer in the atmosphere surrounding the Earth like a little blanket, and when the infrared rays come away from planet Earth, they get blocked by greenhouse gases. These molecules have a special ability to absorb infrared radiation. This little picture here showing some infrared radiation coming past, and bam, hits some carbon dioxide, which is a greenhouse gas, and the energy gets absorbed and gets locked up inside this molecule here. And that means that the Earth cannot cool down properly. So it means it stays warmer than it should do. The heat gets trapped inside. Just imagine it like a little blanket trapping the heat where it shouldn't. It should be escaping and cooling down, but no, it's getting trapped inside. And the theory goes that every year the Earth is trapping that little bit more heat, and every year the Earth is starting to warm up a little bit because of this layer of greenhouse gases around our planet. So what I've just explained there is the theory behind something called the greenhouse effect. And it's the theory that these greenhouse gases are causing our planet to warm up a little bit like it's compared to how a greenhouse works. So a greenhouse is nice, warm and toasty because it traps the thermal energy inside, in a similar way to these gases forming a little blanket and trapping the heat energy inside the Earth's atmosphere. I love showing people this little cartoon from Futurama. It's a little clip here that tries to explain the greenhouse effect in a slightly different way, but I hope you enjoy it too.
Global warming, or none like it hot. You're probably wondering why your ice cream went away. Well, Susie, the culprit isn't foreigners, it's global warming.
Global wobble?
Yeah. Meet Mr. Sunbeam. He comes all the way from the sun to visit Earth.
Hello, Earth. Just popping in to brighten your day. La 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 la. And now I'll be on my way.
Not so fast, Sunbeam. We're greenhouse gases. You ain't going nowhere.
Oh! Ah! Oh! Ah! Oh! Oh, God, it hurts!
Pretty soon, Earth is chock full of sunbeams. They're rotting corpses heating our atmosphere.
How do we get rid of the greenhouse gases?
Fortunately, our handsomest politicians came up with a cheap, last-minute way to combat global warming. Ever since 2063, we simply drop a giant ice cube into the ocean every now and then.
Just like Daddy puts in his drink every morning. And then he gets mad.
Of course, since the greenhouse gases are still building up, it takes more and more ice each time. Thus, solving the problem once and for all.
But...
Once and for all!
Alright, so fortunately today's real-life politicians are way more clever than just dropping a big old ice cube into the sea. So this is a little diagram to summarise the greenhouse effect. So remember that the energy that comes from the sun is called solar radiation, and that comes along and hits planet Earth, warming it up. And then when planet Earth is nice and toasty, the energy is emitted, that means given out from the Earth as a different sort of radiation. That's called infrared radiation. So the stuff that's coming in, called solar radiation, warming planet Earth up. The stuff that's going out is called infrared radiation. And this stuff, the infrared, can be trapped and absorbed by greenhouse gases, which means that they block the cooling down of planet Earth, block the energy escaping, and that will cause planet Earth to warm up gradually over a period of time. Okay, so how do we know about all this stuff? Like, is this stuff that's just been discovered last year, or discovered, you know, how do we understand this global climate change science? Well, I'm just going to rewind a little bit back to 1958. So this guy, Charles Keeling, 1958, maybe when your nans and granddads were sort of, you know, just coming on the scene or something like that. People didn't know about climate change, and people didn't know that the world was going to be warming up over the next few years, and this was an unknown science. This guy, Charles Keeling, is an American. He worked in Hawaii. This was his place of work every day. He worked on top of one of the biggest volcanoes in the world, Mauna Loa in Hawaii, because its altitude and because it's in the middle of the Pacific Ocean. It's a great place to sample the atmosphere and test what sort of gases were in the atmosphere. So he came up to the observatory here and sent little balloons going up into the atmosphere to test to see how much carbon dioxide and other gases were in the air around him. And when he was looking at the carbon dioxide results, he started to see a pattern. And he did this for years. So year after year after year, day after day after day, he was measuring carbon dioxide, and this was the pattern that Charles Keeling spotted. You can see his results start around 1958, and every year he was measuring the carbon dioxide, and it started at this what's called ppm, which is parts per million. So remember, there's not very much carbon dioxide in the atmosphere, so 1 ppm is 1 molecule of gas in every million molecules of every other gas. So 300 parts per million, round about 310 is what it was in 1958, and you can see that every year he measured more and more carbon dioxide, and he was thinking, what's going on here then? Why is the carbon dioxide going up? What effect is this going to have? And this is still being measured at Mauna Loa Observatory in Hawaii even today, although it's been measured in plenty of other places around the world as well. But Mauna Loa is the longest continuous set of data that's been measured about atmospheric CO2 levels, and you can see that it's still going up even in 2020. So we've got the highest. It's gone above 400 recently. You know, in your lifetimes, it's gone from the 300s to the 400s, and now we're about 410, 412. And you can even check on a day-by-day basis. So if I just, hopefully this little link will work. If you go to the website www.co2.earth, there's a little website here that will show you what the level is at the moment. So yeah, 412, that was November 2020 up here. December the 1st, which is when I'm recording this video here, 31st, sorry, it looks like it's at 415, so it's still going up. We can see, looking back a few years, so September 2017, so just 3 years ago, it was just above 400, so 403, 405, 408 last year in 2019, and now it's at 412. So it's gradually going up and up and up, and increasing. So this pattern is now pretty well accepted. It's like there's nobody that argues that carbon dioxide isn't going up. So thanks to Charles Keeling, we know that carbon dioxide is increasing. So basically, when he noticed this pattern going on in the 1960s, he came up with two big questions. It was like, okay, so carbon dioxide is going up. Is that because of something that us humans are doing? Are we making the carbon dioxide levels change in the entire planet? Think about how big planet Earth is and how much air is around planet Earth. Is it something that humans are doing that are making this level of carbon dioxide gas go up? Some people thought it was just some natural, just goes up and down. Maybe it's nothing to do with us humans. Some people thought it was some things that humans were doing. So this was the question back in the 1960s. And secondly, people knew that carbon dioxide absorbed and trapped infrared energy. So they had a theory that maybe this is going to cause our planet to start warming up and change its climate. And that was also a big question that arose from Charles Keeling's measurements. So to answer the first question, is it something that humans are doing? We needed to look back further in time. This data set only goes back to 1958. That might seem a long time ago to you and to me, but to some other people, they can remember 1958. So, it's not that far back in terms of the Earth's history. So one way you can do that is by going to the Antarctic. This little clip here is going to show you how some scientists are drilling into the Antarctic to find what's called an ice core, which is what you get when you drill down deep into the ice and you take out the ice, and inside the ice is some bubbles of air that have been trapped when the snow fell thousands of years ago. So you're basically drilling out some air from 100,000 years ago. And then you can check how much carbon dioxide is in it, so you can see whether the carbon dioxide has changed. So I'll play you the little clip.
One of the things I love about working on ice is it's actually just visually very beautiful. The Antarctic is a beautiful and exceptional place to work. Much of what I do is to try to understand changes in climate over the last hundreds to thousands to even hundreds of thousands of years. An ice core is a continuous section of ice drilled into a glacier or an ice sheet. We're sending this instrument down, which is just a cutting tool, and the thing goes down a meter at a time. You bring it up and now you have these long tubes of ice. Drilling an ice core is kind of like a time machine. You can go back and find out what was the atmosphere like 50,000 years ago. It's snow that has fallen and it then is compressed, trapping the atmosphere. You can count the layers in ice cores like you can count tree rings. And that means that you can actually determine when certain events in climate happened within a few years. A major thing we've learned from ice cores is that CO2 is higher now than it's been for nearly 1 million years.
Eric is my PhD advisor. So there were 7 of us who went down to Hercules Dome in Antarctica this past winter, driving radar around, looking for a place to drill an ice core.
There's a lot of teamwork and camaraderie and excitement about each successful piece of ice that you bring up, because it's a huge amount of engineering and just work to get to that.
I think good group dynamics is also very important because, as you can infer, it's very harsh conditions to live in. Since we put so much time and so much money just to get there, there's a lot of pressure to make sure that it is successful and that we have data to show for it.
We have really practical questions to ask. How quickly is the Antarctic ice sheet going to add water to the sea level and raise the sea level? It's exciting to be involved in research that has direct practical relevance that will actually change how we act and what we do.
I think it's exciting to be a part of such a large question that hasn't been answered yet that could affect so many people's lives.
All right. Right, so those guys were from the University of Washington. This is a clip from this year, 2020. And people are down there in the Antarctic because that is where there has been ice that has never melted for hundreds of thousands of years. So you can't get ice that is that old anywhere else on planet Earth, or not many other places on planet Earth. And that's where the oldest ice is that's never unfrozen. And by looking at those ice cores, here's the results. They've been able to see that the air that is trapped in ice from hundreds of thousands of years ago had less carbon dioxide in terms of parts per million than it does today. So if you look over the course of history from, this is about 500,000 years going back in history here, the carbon dioxide was going up and down between around about 280 down to about 180, then back up and down a little bit, up a bit, down a bit, always between about 180, 280, sort of these sort of areas here. And only since 1950, so in the last 50 years or so, 70 years, has the carbon dioxide level started shooting straight upwards. So it's gone from about 280 in 1950 when my dad was a little toddler. Since in his lifetime, in my dad's lifetime, the carbon dioxide has gone from 280 up to way above 400, and it's shooting upwards, not looking like slowing down anytime soon, is it? So this proves to you that there's something that's happening in the last 100 years that is quite unique, quite unusual, and scientists are almost as certain as you can be that there's something that humans are doing. This is something that humans are having an effect on, and something that humans have only been doing for a very short period of time. In terms of the Earth history, humans have been on this planet for maybe between 200,000 and 300,000 years, but most of that time we were just like what we call cavemen or something like that. So very small communities, very small numbers of humans, and weren't doing very much in terms of building things or driving cars. But and then all of human history, what you might call, like, going back to the ancient Egyptians or ancient civilizations, is probably in this last tiny bit of the graph here. And the only time when we've been burning fossil fuels, which we'll talk about in the next lesson, is in the last sort of, say, 100 years, 150 years. So that's what's making these carbon dioxide levels shoot up, and that's what's made us very worried about climate change. So that's our lesson on greenhouse gases. Key things that we've talked about in today's lesson are the two main gases. The big one is called carbon dioxide, but also methane is also very important in terms of causing the greenhouse effect. You need to know a little bit about the two sorts of radiation. So the one that comes in from the sun and hits planet Earth is called solar radiation, causes the Earth to warm up. The one that goes out from planet Earth to cause the Earth to cool down is called infrared radiation. So one comes in and warms the planet up, one goes out and cools the planet down. Now, greenhouse gases can block the second one, infrared radiation, which means the heat gets trapped inside, and that's called the greenhouse effect. So that's the theory behind the greenhouse effect, and that's why we think our planet is going to be warming up, and is warming up right now. Charles Keeling was the guy that he and his team started measuring carbon dioxide levels in 1958 in Hawaii, and that he was the first person to show in his measurements that carbon dioxide levels were increasing every year, and then to prove that it was something, not just something natural that happens all the time in the Earth's history. There's something unusual going on. There have been teams from many countries around the world going down to the Antarctic to collect ice cores, and that's one of our primary sources of evidence to show that carbon dioxide levels are doing something special that they've never done before in the history of planet Earth, rising at speeds that have never been seen before. So next lesson, we'll talk about the consequences of these greenhouse gases, what changes that's going to cause to our planet, and what we can do to maybe slow down those changes or to reduce the effect on planet Earth climate. Thanks for listening. See you soon.